Hello again. We are going to be covering objective number 9. So I am going to be using a whiteboard, and we are doing this distance learning, and hopefully I will not be as nervous as I have been in the past. So let's get started with the whiteboard being the center of attention. Hopefully this is working. I have done a complete video watching the camera, and everything appeared to be reversed image. So I wrote everything reversed image and watched the whole 20 minutes and realized it was just the camera. It would be reversed image for you too, not just me. So let's just get started. Remember how we talked about the emitter, the base, and the collector? And so what we're looking at is we know that on the emitter is if the current is going to flow through this device, 100% of it will flow through the emitter. And when we look to see how we control a bipolar, it is controlled by the emitter base current flow. So only 3 to 5% of the current is going to flow, and I can't read that, I'm sorry. 3 to 5% of the current is actually going to flow through this base. The other, or the rest of the current, because it all has to flow somewhere, but the rest of the current is either going to be 95 to 97% of the current is actually going to flow through the collector. So basically what we're saying is this idler current here that we've always talked about, this is current controlled by the emitter base current. This is turning on this device. And then the rest of the current flow will be flowing up through the collector. So what we're actually looking at here is we're looking at a device that we can turn on and turn off with current. Also remember, I'm going to go ahead and erase the emitter and the collector and the base symbols because I need those spots to write on. And this is a small board. You know I like lots of board. So what I'm going to do is we're going to give some arbitrary values. I know you should remember, hopefully, if not, go back and look how we have calculated. We had things like this where we did the calculations. Do y'all remember this? I hope so. And so we said that we have the emitter resistor, the collector load resistor, and I'm getting out of the board, out of there, sorry. So we have all of these values here. And so when we look at that, we were actually doing voltage drop. So this plus this equals the source voltage. Remember that. I'm not going to go too far into this. I just want to do some refresh of memories. And this plus this and this plus this plus that. Okay. So now erasing that, we're following that same concept. So what I'm going to do, though, is just give some arbitrary values to this particular device here. I'm going to say, okay, in this particular case, let's just give this emitter an arbitrary value of 1 volt, just because it sounds good. And it's easy for me to work with. Well, I know the base is always either going to be 3/10 of a volt or 7/10 of a volt higher than the emitter, because that's all that's dropped between the emitter to the base. So in this particular case, I'm going to make it silicon because we use that the most. I'm going to make this a 1.7 volt drop there. So that just tells me that the base is always going to be a little bit higher than the emitter. The collector, though, is going to be higher than all 3 of them. And if I don't have a collector load, which I don't have to have, I could drop the whole source voltage there. But let's just say that I'm dropping 8 volts here. So that means that 8 volts, it would be the 1 plus this gives me the 8, correct? So that would be 1 plus 7. So that would be the 7 here. Do y'all remember that? Okay. I'm saying you shook your head yes, even though I don't see you. So that's what we're looking at here. Now, we talked about, in the last session that I got on, we talked about configuration characteristics. And we talked about how to tell if one was common emitter, common base, or common collector. And I am doing some review here because I know that I need you to remember, and some of you probably didn't watch all of it because I'm so entertaining. But let's look. We said that if we had a common emitter, common base, common collector, and I am going to write this over here on the side, and hopefully this marker will last this full time. I'm going to make a little chart here, and hopefully I stay inside the bounds. I went outside the bounds just a tad. Maybe if I slide the board just a hair. Okay. Then I can stay in bounds. Okay. I am new at this, you guys. You're new at this, hopefully. So you will be forgiving, and you will know that I am trying really hard to make this work. Okay. So we're using our chart here. And I think I got too many lines, but that's okay. What I did is I just drew a graph. It's something similar to the handouts that I handed you before, figure 26, and then there was 2 other sheets with it, one on the back and things. But what we're going to do is look at these. So I'm looking at those, and I'm going to look at a common emitter first. I know that those sheets usually list a common base first, but I'm looking at a common emitter. And I'm using the initial CE because I don't have a lot of room on this little bitty board, as big as I write. So when we look at it, what it means is it's a common emitter. That means the emitter is common to the in and the out. Okay. Well, I also remember something else, Ohm's law here. And so remember that the bigger the resistance, the more the pressure to push less through. Y'all remember that? So if it's a larger resistance, that means a smaller opening, then it takes more pressure to push less through. And just to see if my color changes will happen here, if it'll make any difference here, I'm going to do my other one in a green, but I'll do it on the other side too. The lower the resistance, that means the bigger the opening, and it shows up a little bit, we take less pressure to push more through. So what we're always saying is that the voltage and the resistance in normal operations are proportional, and the current is not proportional. I lost the word here, okay, to it. So we're going to use Ohm's law and the stuff I have here. And then we're going to look at the common emitter. That means this emitter was common to the in and the out, like we talked before. So that means that if I have that happening, that means that my in, this is the common point, and I want to look at the unique points like I did on the last video. So my unique in is on the base. Okay, and I need to pull this in a little bit. So this is my unique in. So really it's in between the base and the emitter. My out is on the collector, my unique point. So again, actually, it's between these 2 points and these 2 points. So I want to look at some things here. And I'm trying to figure out what my current gain and everything would be. So I'm just going to list I here. I'm going to list my voltage here. I'm going to list input resistance, and I'm going to use the ohm sign. And my output resistance. Remember the points that are common. So in this particular case, this one's my common point. So when I look at it, I look at the current. Okay, unique first. This is going from 3 to 5% to 95 to 97% of my current. So basically what it's saying is I'm going up in current. So I have a high current gain. So I'm just going to put the letter H here for high. Okay. If I'm going to look at my voltage, I'm going from 1.7 volt to 8 volts. So I have a pretty high voltage gain, right? And some people might say that it's very high. So we're going to put a high voltage gain here. The input resistance, though, since this is my common point, it's only right here. So whatever the resistance is of the emitter and this value that drops 0.7 is my input resistance. So that's going to be low. In fact, it's going to be considered it's just going to be a moderately low or a low value. So I'm going to put low here, L for low. The output resistance, though, is across this whole thing. So that would be a very high resistance. When I consider this to this, that's very high for the output resistance. Okay. Okay, so if we look at this, we can kind of see what happens with the current voltage, the input resistance, and the output. But what happens when we have a common base? So I'm going to put the common base next. I like the common base because it's usually the lazy one and it lays down. But in this particular case, it's not going to. Okay, so we know the base is going to be common. So this is going to be common between these 2 points. So my N is going to be coming in on the emitter. So here is my N right here. Now, if my N is there, then my out's going to be here. And I apologize, my dog is barking. Let me see if I can get him to quit. Well, hopefully me holding him will keep him from barking for a minute or so, but I don't know that it will. We'll try it and see. He's not much of a spoiled brat or anything like that. He's just a spoiled lap dog. Okay, so let's look at this thing here now. We are actually doing the common base, and we're coming in and in. So what I want to do is I actually want to take and say, okay, the current. Let's compare this current to that current. This particular current is 100% of the current, where this is 95 to 97%. Ooh, you know what that means? We have a loss in current. So actually what we have is an alpha. And so if I can write the alpha sign right, that one didn't turn out right, but let's see what I can do with it. Hang on just a second. Okay, so this is the alpha for this particular current because it's a drop, it's a loss, it's not there. The voltage is going from 1 volt to 8 volts. That's a pretty high gain. That's probably the highest gain you can get out of configurations. So some people will call it very high and some people will call it high. But to me, I think going from the minimum to the maximum is pretty high. So I'm just going to put high for now. And like I said, some people will call it very high, and I will put that kind of in dotted letters here so you'll know some people call it very high. But I call it high. It's somewhere around 600 to 800 times bigger. The input resistance now is only across here again versus here. So the input resistance for this particular device is very low because it's actually just going to be this emitter resistor, whatever it is. So this is a very low input resistance. On the output resistance, though, it is going to be across all of this stuff, and so that is going to be high. In fact, in my mind's eye, it is a very high output resistance because we're across the whole thing. We're across this whole transistor. So it's somewhere probably around 300 ohms. I'm sorry, 300 k ohms or so for the output resistance. Okay, let's look at the last configuration and look at its characteristics. And that's the common collector. It also can be called the emitter follower. All right, so if it's the common collector, which lead is common? You are correct, it is the collector. So that means in that particular case, on the common collector, this and this are common. So the N is coming in on the base, and it is coming off on the emitter. Is that correct? Yeah, that's right. So in that particular case, now let's look at it. I am going from 3 to 5% of my current to 100% of my current. Oh, you know what? I have a loss in current because I have more current here. I'm sorry, I said that wrong. Voltage. I'm looking at the 1.7. I'm going from 3.5% current to 100% of the current. So I have a very high gain in current, not a loss in current, a very high gain. Because, I mean, I'm only got like 3 to 5% depending on the transistor. And now I have 100% of the current, so I have a very high gain in current. It's the voltage that I have the loss. I'm talking 1.7 volt to 1 volt, so I have a loss. So now in my voltage, I have an alpha in my voltage gain. So now, if I can write this thing correctly, I have my alpha there. Some people write it a little different than that. Now, looking at the input resistance for this particular device is going to be somewhere between, I don't know, we're coming through here. So we've got part of this reverse bias junction here. So it's going to be kind of a high input resistance. I'm going to say, I don't know, around 20K to 100K. So this is going to be a high input resistance. The output resistance, though, is here. Basically, the output resistance is going to be whatever that transistor has here, this resistance here. So that's going to be a very low output resistance because it's only across this one resistor that's there. I can tell you in this particular case, whenever I have my output coming off the emitter, whether it's in a common collector or if I have the input coming here, I have to have a load here because I cannot put something in from ground. Remember, the emitter could go straight to ground. Not if it's going to be used in a common base or a common collector. Only if it's used in a common emitter. Okay? So this is actually the way this is going to flow. So, again, looking at the resistances we have, and I think the chart here will say that this is just low, not very low, because these two here. But this is the chart that we're developing. So if you actually take your figures here, and you will look at this, I know you have a figure 26 like this, and then you also have on the back of it is this one, or if it's online, you would see this. And it just has a chart here. It has values of numbers in there, as you can see, and when you look online, you will see that. But it's not those numbers so much that I'm worried about. It's actually knowing that it's higher or lower. I'm actually going to say it's higher or lower on the test. I just want you to kind of have an idea what's going on. So to summarize, what I want you to see is you can look at the DC here. You can look at the voltage drops. Just give some arbitrarily. Always know that this is the lowest value. This is going to be 0.7 or 0.3 higher. It doesn't matter. And this is going to be your biggest one of all of these. This is always going to be 100% of your current that has to flow through the emitter. That emitter, it gets into the junction, it divides up, and then that primer current or that base current that turns this device on, 3 to 5%, that's not 3.5, that's 3 to 5%, will flow through the base, and that will allow the other 95 to 97% to flow through the collector. So comparing these points, you can actually come in here and derive this chart, and you can look at those configuration characteristics. Because the configuration characteristics are going to be used for the AC component, it doesn't matter. Because what I do is I get this over here and I put that AC on my DC. It actually is going to be pulsating DC, or a DC with an AC component, however you want to see it. So it's not going to really change it, the reactions when we put that signal on there. It actually is going to follow this because it is a DC with an AC component, or a pulsating DC, if that's what you want to call it. Okay, I hope this helped. This is covering Objective 9, and I will be back to cover some more.